I'm Joe Zrelowitz. I'm a professor at CU Boulder, and I have the privilege of introducing Samir Raizada. So Samir is an architect in Verizon Media's performance engineering group with more than 10 years at the company. He explores new technologies and their applications for the company's workloads and evangelizes these technologies to their numerous properties. He's been working on the evaluation and application of 3D crosspoint and persistent memory for real-world use cases for about 3 years now, and we're looking forward to hearing about them. So, Samir, I'll let you take it away.
Hello, everyone. Hope you all are doing great. Today, I'm going to talk about driving technology in the context of persistent memory. I'll go over my journey of driving persistent memory forward at Verizon Media, and I'll share my approaches, learnings, outcomes, feedback, and I mean, this is more from real world use cases with the community here, and hope this will be useful for everyone. It's going to be fairly non-technical with bits of high-level information as needed. And my content here is mostly in context of applying technology to the large-scale web applications. So a bit about myself. I'm working in performance engineering group at Verizon Media for more than a decade. And here I've been evaluating technologies, products for their feasibility, analyze TCO, and guide properties in real world applications and running in large scale production environments. And based on these technologies and applications, I work with architects and build hardware solutions and evangelize those. And when such solutions are in production, I also do hardware and software optimization, analyze performance, and provide feedback and improve TCO. I have been working on persistent memory and its use cases with a lot of different properties for a few years now. And in the past, I have worked on embedded firmware, device drivers, and application software. So let me start my perspective by talking about technology innovation. And again, this is in context of server or computer hardware and software. I took this definition from dictionary.com, and basically it is introduction of something new or different. And to simplify for myself, I first categorize technology based on 3 parameters. So impact, ease of adoption, and cost. And here to illustrate, I'm just showing in 2D, but you get the idea, right? So, so there are 4 quadrants here in 2D, and you can think of cost as the 3rd dimension. So we definitely want to incorporate technologies that are high impact, easy to adopt, and low cost. So those are no-brainers. And these end up becoming mainstream in the long run. And we want to invest in these technologies or technology changes. And on the other hand, we don't want to invest in technologies that have low impact and hard to adopt and cost more, right? And these will have low adoption and have niche market and probably will be replaced by something else in the future. And so for simplicity, I lump these into incremental and disruptive changes in technology. And this is important because we have to figure out how much investment we are going to make in technology and in terms of effort and resources. So typically incremental are easy to adopt with lower benefit over previous technology, implementations, or products. So for example, um, for capacity improvements in hard drives, we have been adding platters, and there have been improvements in recording technology. But the underlying media is the same, and from application perspective, there is not really a huge difference in characteristics. They write the application same way for sequential I/O, or optimize for sequential I/O, and try to reorder your I/O to optimize that way. There have been some bigger changes, um, like SMR, or actually SMR I categorize under the low benefit or lower benefit or niche product. But the point is that this is from application perspective is non-disruptive or incremental change. And on the other hand, disruptive are typically harder to adopt or have other challenges or other considerations, and have better ROI. So an example of that, this is magnetic media going from technological change, going from magnetic media to NAND flash based media. And think of an application of this media in drives. It had completely different characteristics and needed a new type of controller, and adopting it into storage devices took a long time to mature. And even from an application perspective, it provided a new tier of devices. Um, I mean, it is a different magnitude of difference in random I/O performance and trade-offs in the amount of writes. And it had to get best out of these. There were changes in the platform and software, and in fact, there are storage solutions specifically built and are being built for taking advantage of the media. Note that adoption challenges is actually in building products with these technologies. And as you go higher layer, people won't even know or care what it's running on. So to build a seamless product with with a significant cost or TCO advantage, there's a great deal of research work needed to use the technology innovation. And in fact, for NAND-based drives, application considerations are also important. I mean, once you have the application ready, the users of the application won't even know. Now, for an application to adopt a new technology, one has to consider trade-offs. So, for example, where does it improve efficiency or performance of my product over alternatives, and under what assumptions? So keep in mind that I can implement a solution with the same set of features using several different technologies. I can use a mix of uh, memory and let's say hard drives, or persistent memory and hard drives or SSDs, right? But my cost and performance is going to vary. On the same note, what are the features that the new technology change is going to provide for the application? And what features is it going to, or I have to give up from my application perspective, right? And does it give me competitive advantage over other solutions? Or where do I do trade-off there? Is there some place where I'm losing competitive advantage? So in a sense, where do I target my application? One important choice that application owners need to make is whether to invest in a new next cool application or develop a new feature. So effort involved in adoption might be bigger if there is an architectural change. And the amount of regression testing that needs to be done when you make an architectural change, I mean, even if you just introduce a new technology, there's a lot of regression tests that needs to be done for large-scale production applications. If you look at some of the products, you will notice that they skip a number of incremental generations for technology. And example is like skipping certain CPU generations, or maybe skipping incremental hard drive capacities, right? And um, use that time or resources to come up with new features. So for hardware as a platform for software, we consider efficiency, cost, and performance implications of the platform itself before adopting those. For any new technology, there are challenges when trying to get adoption for various use cases. Often, I'm excited about a cool new technology, and I go to the application owner with a use case. I get asked, am I going to be the first one, or has anybody else used it in the past? So they don't want to be woken up in the middle of the night with their application breaking because of this, right? And basically they want maturity of the product. They want to trust the product before they adopt it, right? And another important factor is having clean process to integrate or the hardware solution or the software solution or the technology, right? And having a common standard irrespective of platform use, right? I don't want my applications to be running on one vendor servers and not be able to run on another vendor servers, because that is locking, or not have a clean process to be able to integrate technologies in a different set of different vendor servers, right? So if product is targeted for a small scale and has specific niche market, these things don't matter. But for large scale adoption, this matters. For architects and developers, complexity of implementing a solution based on the technology is an important factor. More complex the solution, higher the risk of not being able to deliver on time, or worse, having problems later. Actually, another consideration that is on the timing of the technology. Now, again, this kind of ties back to what I said earlier. Skipping a generation, skipping a technology change, just because there's something better coming in the near future. And the last point is, of course, an important one is cost, right? And it's always going to be cost and TCO that at a large scale, it matters. For a small scale use case, changing cost by 10% doesn't matter. But when you are spending billions of dollars on infrastructure, 5% increase is huge deal. All right. So switching gears, it's about 7-8 years ago. I remember there were companies bringing us the idea of NVDIMMs, their solutions, presenting their solutions, and these were DRAMs with flash and battery backup. So in the event of power loss, in-memory data is written to the flash, and later there were a couple of implementation to place flash on the memory bus in the hope that this will reduce the latency for IOs. Now, both of these solutions had adoption challenges. These were not compatible with mainstream platforms or had non-standard, unsupported modifications to the BIOS, or um, I mean, there were some code or some firmware update that you need to run, which need to be maintained. And it's definitely in the long run, it doesn't make sense to run in large environments, just because something will fail and you will not have a solution. And now you are with thousands of servers without any way to keep them running. And on top of that, these also had significantly higher cost. And so for large scale deployments, these were not practical. Nevertheless, these jump-started the software and hardware ecosystem. And then when Intel and Micron announced the 3D Crosspoint media, and when Intel came out with the NVMe product based on this, we were excited and we evaluated it. It had better performance characteristics than NAND flash-based NVMe devices, but it wasn't as attractive just because of the limitations of the interface and capacity um, trade-offs, I guess. And it provided incremental benefit over higher and enterprise NVMe products. And it only made sense if you needed very high endurance, so you kind of needed lower capacity, and or cared about reducing latency uh, to bit less than half for your IO. Now, when we evaluated DIMMs, the persistent memory DIMMs, the advantages were clear, and we were very excited about the performance in terms of latency and read bandwidth. And that's when we started exploring opportunities with the applications. So a quick note about supported modes and how it kind of relates with how much investment we need to do in the product, and how easy is it to adopt, and um, development efforts involved. So memory mode kind of is an incremental change. Your application can run without any modifications or minor modifications, just because you might have to use, let's say, off-heat memory or more off-heat memory, or your application settings will change. But you lose one of the important characteristic of the media, which is persistence. So low barrier to adoption, but you lose something. And then app direct mode needs architectural or major code changes in order to adopt and get real advantage of it. And it may have higher impact for the applications. And actually, one easier way is using storage over app direct, which is kind of like memory mode in terms of the effort needed. And so, like memory mode, in general, it's mostly the configuration changes that are needed here. So now looking at the adoption opportunities, and assuming certain size, latency, cost advantages for such products, and I mean other persistent memory solutions that will come in future, not just the products based on cross-point media, we would want to apply these where we can reduce the complexity for the software, hardware, and architecture. And this will help in reducing the development and maintenance cost and risks. There's also a possibility to reduce infrastructure by eliminating certain layers or having smaller footprint. And this will again impact the complexity and TCO. We can also apply technologies to improve the performance, where we can get better user experience, and will affect the revenue and have better ROI for the product. So these are kind of the use cases or the way we were looking at looking for products in general. I mean, looking at products in general. A straightforward use case for for persistent memory, uh, assuming that there's a large size, there are large sizes available, and it costs it has better cost structure, is for applications that require or can take advantage of large memory footprint, and which may lead to consolidation in some cases, or um, um, may be able to run bigger jobs, right? And it's very easy to adopt since it can be accomplished with memory mode. An important use case um, that we were looking in our infrastructure was using this for saving application state and enabling faster application restarts. This is a pain point just because there are some use cases where it takes several hours, and in fact there was one which because it's a distributed application, uh, restoring the application state and restarting the service actually takes several hours, I mean even up to date actually. And in fact, one of the use case we saw last week in a keynote by Doug, this was about Oracle times 10, where application restart was much faster with persistent memory. This is definitely a use case that we see as an opportunity. Then applications that are bottlenecked by latency of IO operations. For example, wall files or write-ahead logs for NHBase. So speaking of these operations will improve the throughput of the application, and hence either I can serve more or need a smaller footprint. And I think peering is an important application of persistent memory, and there's a lot of opportunity there. It's harder to implement, and it's a bigger change from application point of view. Um, Developers and architects don't really want to deal with it. But since there's persistence and high endurance, it can provide performance advantage as well as preserve the underlying media from torture, right? I have a good example here for which I was looking for a solution. And as I said, I mean, the application owners don't want to touch it, or the architects don't want to touch it. So for Kafka, since the write rates can be high, and because of the persistent requirement, it can put a lot of strain on the SSDs or the underlying media. In fact, we switched from SAS drives a while ago and moved to SSDs for performance, and there were trade-offs though for wear out, but we moved just because we can absorb more traffic or more topics and throughput. So incorporating persistent media can solve these problems. So it can improve the performance as well as because it improves the latency. And it also um, takes care of the wear out characteristics of the media. So underlying media can still be SSD or hard drives, right? But because we need the persistence, just because you don't want to lose any of the data. So Kafka is a messaging service, and you don't, even though you might have two copies or you might have multiple replication factor, but you still don't want to lose any data, and you want persistent. Even if the whole cluster goes down, once it comes up, you still have your messages. So Once we have these applications or application targets or opportunities, we want to target these applications, and we want to overcome the challenges for these application owners by making them familiar with the persistent memory and its trade-offs and showing value. And we enable them by providing hardware and software resources and motivating them and supporting them along the way as they build the solutions. So one approach and a successful one we took early on was to accelerate the product innovation in incorporating persistent memory, and to create awareness was organizing hack events. We informed developers, architects, and management on the potential of persistent memory, and sending out potential use cases and how this media provides benefit and value to the application, not just cost, but performance or something that they cannot do before, something that was their pain point. We had webinars and selected materials published so they can refer to it and establish for themselves the value for the product and the technology itself. And then we targeted applications that had pain points or clear advantage of using persistent memory, and then had hands-on workshops and brainstorming sessions to, in collaboration with Intel, and Intel was a great partner here, to discuss and come up with additional project ideas and take advantage of persistent memory. We supported the development efforts by providing guidance and support and helping the architects, developers with identified problems and gaps in their solutions. And then most important part here was recognition and its motivation that the developers and architects had. So we scheduled time for demo, and it was kind of fixed time just because we don't want to go back and forth on providing more time and causing confusion. In general, we had some problems because of that, and I'll talk about that in a little bit. So we had evaluation of these based on value for the business. So again, going back to the three dimensions of cost, impact, and ease of adoption. So there is the evaluated based on financial or business impact, and feasibility or ease of adoption, and performance impact, which again affects the cost. Another factor that we considered, which is not here on the three parameters, is how mature the product was, or how mature the result of the project was, and how complete it was in terms of considering the other components of the architecture and level of integration with those, and basically whether it was ready or how far it is from actually deploying in production. So I'll briefly talk about a few examples of work that was done. One of the projects was to create persistent cache of folders and metadata of the end users for a web application. Here there was a significant improvement in performance, about 10x, just because on an average, just because most of the data was served from the cache. There was slight overhead for the first set of calls, but in general, on an average, there was more than 10x improvement. So this also reduced the load on backend, and which was another advantage. And here we didn't compare the performance with other caching solutions, and for the right reason, actually. And but there might be still the performance improvements with just using NVMe or other persistent media. But maintaining a persistent cache and keeping it updated with constant changes can be very challenging with other media. For example, SSD or hard drives. You can have a cache, but keeping it updated is a challenge, because the operation, I mean, a single change in metadata can cause a full block of data to be modified or committed, and this will cause a huge load on the media, and will also increase latency. And in fact, SSDs will probably wear out if we use those for caching and actually have this much churn. And the main challenge that we had here was overhead of serialization and deserialization of data while using the libraries, which seemed redundant. And this was Java applications. And and for a low latency distributed key value store, one of the project was to compare performance with NVMe SSD for various request sizes and number of instances. So here we found that smaller records, for smaller records, we saw latency advantage of persistent memory, while the latency for NVMe based solution was 50 to 100 microseconds in 50 to 100 microsecond range. Persistent memory was in 1 to 10 microsecond. And on throughput, we got almost 3x. And here, this was actually using storage over AppDirect. And the challenges that we faced here were for larger records. And as you increase the size of the records for the store, the difference between the performance of NVMe and persistent memory was harder to notice. In fact, for very large sizes, there was bigger slightly bigger latency hit on persistent memory, and that was at 99 percentile actually. Yeah, I think I already mentioned that this was using storage over AppDirect. Another project used persistent memory to improve journal write latency. So in the original implementation, the journal was on a flash device, which had latency and endurance limitations. And since the writes needed to be flushed often, using persistent memory, you were actually able to do constant flushes, and it also improved because of latency considerations. We were also able to improve the performance of the application by about 5x. And this had significant TCO impact over the previous generation of servers. And this was just using storage over AppDirect. And I mean, it was mostly configuration changes and slight changes to application. Just, I mean, nothing major in terms of architecture. And here we had to spend a bit of time finding finding reasonably good application and platform parameters for running the application. So what would have helped is, having having data on the performance and file system parameters, or sizes of for what sizes of I/O operations, what settings should be used. So kind of comparison would have helped to have spent lower time, smaller amount of time and effort on this. I'll briefly mention, actually I'm kind of close on time, for applications that deal with, there's an application that deals with application matrix. So this is kind of monitoring application, and it has millions of writes per second per server. And the idea was to build and persist data structure in persistent memory, and this was a TSDB, or time series database data structure that we want to keep updated and keep in persistent memory. I'll skip the last one, and yeah. So anyway, so after these events and collaborations, we have been doing additional work with properties and application owners, and there have been a lot of progress. And now there's always a consideration to persistent memory in building new solutions. So going to with all this journey we had, what were the learnings? And I kind of alluded to all the challenges we had, and I highlight some of these points here. The experimental support for some of the languages is a challenge. Was a challenge. So we found, actually Python specifically, and we also found inefficiencies in persistent memory enablement software or the libraries. So I already mentioned about serialization and deserialization required in some of the libraries, and there's a lot of garbage generated when you use JNI, for example. Some of these have been solved. So when you create an object, there's actually another library that was based on this feedback, Intel made modifications and they released the library. And then there's what would have helped is to have insights into memory access patterns. So having kind of a heat map of you know, how much is my hot memory? Like, we have it for I/O, but not really for memory. All right, so this is more for us in terms of processes, and when you have these kind of efforts, one thing to realize is that it always takes more time and effort than you actually think it'll take. You also want to have a balance here, and you want to keep time long enough to be able to do these projects, and short enough to not lose focus. So in fact, I bring it up because we actually had almost 20 different ideas that went into the hack event going in. And those were, I mean, there were actually even more ideas, and we had noted almost 50 different possibilities. But the point is, the changes and the problems with the process and support was a big factor in getting only 5 or 10 final products improvements, and the rest were actually were done later. So when there's a bigger change, when there is a disruptive technological change in the applications, we need longer upfront engagement and guidance to the architects and developers. And we also need to do frequent check-ins and to keep and reviewing and making sure that there's nothing um, um, wrong with the architecture, or uh, there is no blockers. Then we also want long-term support, which also needs resources. And one of the important thing that we found was, and that was the reason why a lot of the uh, projects didn't complete or dropped out, was executive support and establishment of ROI. The challenge was that the they had other priorities, and the teams had other priorities, and their executives didn't um, focus more on the other priorities and not on the project itself, and so they didn't have enough time to build the product. Oops. All right. So feedback to the community, and just want to share my final thought here. So we should drive towards commoditization of persistent memory, and for which we need to add support to wider hardware platforms. And I'm sure there's a long-term goal here, but I just want to highlight that. And we should also target uh, providing better cost and compelling TCO advantage, and not just have this as a niche technology. And this will in turn improve the infrastructure and again improve adoption. So this is kind of a cycle. For wider adoption, we also need to have solid production-ready software infrastructure. It makes sense that initial software implementation and infrastructure was mostly for C, C++, um, and for applications running at lower levels for building hardware solutions. But for large-scale web applications, we need solid and performant libraries for languages like Java, Python, and Go. And Java support was supposed to be in production ready when we were experimenting, and still we found a lot of performance issues, and I kind of stated some of those. And AI/ML, as it gains wider application, we need solutions and frameworks to actually automatically support and exploit persistent memory. We also need platform improvements to have feasible, large-scale turnkey solutions. It would be ideal to have like a platform understand and take care of the volatile and persistent requirements of the application. So the application doesn't need to be architected, or there should not be any code chain needed, and that's the best case scenario. But even if we can get closer to that, it will help in the adoption barrier, and will increase the adoption of the technology. And last point is, although I have seen a lot of collaborations between academia and industry, I think there is scope for more. There are a lot of open problems in this area in production environments, and this is an opportunity for everyone. And I thank you. Sorry, I ran over a little bit.
No, thank you. Thank you for the wonderful talk. At this point, we're going to open the floor up to questions. We've got a couple in the chat. If you have questions that you want to queue up, I'd welcome in the chat, and I'll go ahead have some people who've already asked take the floor. So Jack, I think you had a question.
Yeah. So okay.
So I guess I'll ask it for him then.
Context.
So the question was, what applications that you saw at Verizon that could benefit from persistent caches?
So this specific application was user folders and metadata. So they think of it like this front end that deals with and queries backend for let's say folders or metadata, messages, metadata, and things like that. And this specific application, um, if we build persistent caches of because users, I mean, same users do the same kind of behavior, right? Opening the same folders or messages or recent messages and things like that, right? So um, having persistent cache um, improves the latency for the end user and also um, reduces the backend load. So that's the idea. And keeping it updated is the key here. Having persistent memory actually enables to have enough performance and and endurance and um, to actually keep it updated.
Chun Liu, there's a question in the chat if you'd like to ask it.
You mean ask myself?
Yeah, go for it. You have a
Sure.
conversation.
Right. So, and you mentioned here that you're thinking about to improve the AI or machine learning frameworks. And if you look at the question, the use cases before, can you see which portion require improvement? Because if you look at it, yeah, go ahead.
Yeah, I mean, kind of ties back to Python, right? So a lot of the AI ML frameworks and a lot of data scientists mostly work on Python notebooks, right? And the limitation there is the amount of memory, right? Anything that fits in memory is something that you can work with efficiently. And anytime you have to go out of your memory footprint, there are libraries that enable. I'm forgetting which one, but you can actually use uh, something from your storage also, but the data from your storage also, but it's not efficient. So that's an example of why what needs to improve. Now you can argue that memory mode is one possible solution, but there are trade-offs there, and as I explained, it loses persistence. It also reduces the amount of memory you have. I mean, you can still, I mean, you in that case, memory acts as level 4 cache for all practical purposes, right? And so you um, you want something better than that, and I'm just suggesting that there are opportunities there, and looking at some of the use cases, um, there were use cases where we had one application requiring, and this was a while ago, requiring 6 terabytes of data, and now persistent memory enables it, but how efficient is that? And also the considerations of garbage um, and overheads come into picture here. Right? These jobs, these analysis, and I mean, probably for training, it's more important actually because it takes a long time. And inference, not. I mean, typically it's not as heavy, so or should not be as heavy. But some of these jobs run for multiple days, right? And having improvements there, I'm sure that there are places where we can improve. And I looked at one time at how the memory accesses were, and it's not optimal. And again, this goes back to one of my points about having visibility into memory, I guess heat map of memory accesses, right? That'll help. And it's not an easy problem, but it's something that is interesting. And just because there are also going to be other interferences with your application, so that's another consideration. And you need, it's a hard problem for applications when you have multiple pieces of software running, and you don't know which one is actually interacting. It's not easy to figure out for a developer or an architect, and we need to get involved and to get collect a lot of data to figure that out. So
right. I have a follow-up question regarding that. Do you see the persistency, the property of persistency, would be anything useful for AI or machine learning?
sorry, say again.
The property of being persistent.
So for example, if your job runs for 2 days, and you let's say your job dies after like 1.5 days, it definitely helps.
Yeah.
If you're
checkpoints,
if you have to update your model every day, and yeah, I mean these are considerations. So you might miss your SLA to update your model, right? I see 2 more questions. I think you talked about decent. This was from Jim. You
Yes.
talked about some decent performance in increment. Sorry, I don't understand. Jim, can you please ask? I'm missing something there. Maybe. Oh, write heavy. So did you have any experience with write heavy workloads? So actually, write ahead log is in fact, things like Kafka or these are mostly write heavy workloads. You in a lot of cases you actually don't even read the data from the media. I mean, for logs or journals and things like that, you write it and hope that you never need to read it. And same thing for Kafka or messaging services like that. You write the data, and when typically the topics will be consumed within 5 minutes, and the data is most likely in your memory already, so you don't really need to go to the media to read it. So in effect, these are actually very write heavy workloads. And in fact, you have to flush. So these have a big impact on endurance of the media.
Yeah. The other question I think is also relevant. And let me put some words around it. As product people or as developers or engineers, we get very excited about technology. You're on the sharp end of the spear trying to figure out how to implement this technology. So, one, why was this more interesting than some of the other things you could spend your time on? And 2, do you think in your experience that it's going to take, the same amount of time as something new to adopt, or maybe a little longer than average? What's your take on this, on the status of the technology itself?
So one of the important consideration is stability of the technology or maturity of the technology, and the infrastructure around it. I think that's the point that I raised on the maturity of the software infrastructure. Technology itself is mature, and for an application that is written in C or C++, I think there is enough flexibility to build solutions or build efficient solutions, right? But for a Java application, there are still holes just because the way, and I'll give you an example of one of the applications. And this was an evaluation for in relation to off-heap memory. So this application had sharded memory just so there is no locking involved, and so the libraries in for persistent memory in Java didn't support sharding. So basically, all of that is one monolithic chunk of space that needs to be managed, and which means that now I introduce locking. And this application has I think 7 million operations per second, and once you start locking, and that is the bottleneck. So to summarize, I mean, the point is that the software infrastructure is not mature enough to have large scale adoption. There are still places where a lot of work needs to be done. The performance and characteristics of the libraries and tools have to be characterized, so we know what to use and what are the trade-offs. And it's a harder problem, just because you don't really want application architects and owners to go through and try out everything, because it's too time consuming.
Yeah. Thank you, Samir.